Hi, and welcome to the 22nd webinar in 12D's Industry Solutions webinar series. My name is Lisa Stewart, and I'm the Marketing and Communications Coordinator at 12D Solutions. Our Industry Solutions webinars are designed to provide insights into overcoming challenges in an evolving industry in more effective and efficient ways. We'll keep running these webinars regularly and recording them for posting on our YouTube channel with links through our website. Our first 21 webinars from this Industry Solutions series, as well as 21 webinars from our training series, are available online if you missed those. During this live presentation, you'll be able to type your questions along the way, as shown on the screen, and we'll answer as many as possible throughout the webinar. At the end, I'll also read out some of your questions to the presenter if there's time. Today's webinar, Dynamic Water Supply, will be presented by Jeff Thompson, who has been a Senior Water Resources Engineer at 12D Solutions for around 10 years. Jeff has a total of 35 years of involvement in civil engineering software and was the co-founder of XP Software, which he directed for 25 years. This webinar will provide an introduction to Dynamic Water Supply, a new module in 12D Model 12. This module completes the trilogy for three waters: stormwater, wastewater, and water supply, and allows hydraulic analysis and analysis of water quality behaviour of pressurised pipe networks consisting of, for example, pipes, junctions, pumps, valves, storage tanks, and reservoirs. It can perform static analysis, but this demonstration will mostly focus on dynamic analysis. Over to you, Jeff.
Yeah, thank you, Lisa. So as Lisa just said, the Dynamic Water Supply module completes the three waters trilogy of sanitary sewers, steady state and dynamic stormwater, and now static and dynamic water supply. Now, dynamic just means there's a time component, like hydrographs versus peak flows in stormwater. So in rational form, we would have a peak flow. In the dynamic drainage analysis, we'd use hydrographs. In water supply, we can either have a static analysis or we can do an extended period simulation where time's involved. So we're going to focus on the extended period simulation today. So DWS is a 12D module that can, as I said, can perform both static and dynamic analysis of fluids in a pressurised pipe network. Now typically that would be water, but you could also use it for any incompressible fluid like oil or petrol or liquid natural gas or whatever. Okay, now the DWS module is really nice because it's the simplest product we have in our water engineering suite. If we're going to analyse or design a common water reticulation system that we'd use in a subdivision or a commercial development, the data requirements are minimal. So you find that all of the 12D trainers will be able to tell you everything you need to know about dynamic water supply. But, and these are the things I'm not going to focus on today, should the need arise, you can also model, for example, chemicals. So you could model chlorine residual in your system, or you could track the propagation of contaminants through your network, or you could track the age of water and look for dead zones in your network, or you could track, if you had multiple tanks, you could track the sources of water and how much water is coming from which tank or reservoir. You could also use the software to optimise your network. So you could optimise water sources where you've got multiple tanks. You could optimise pumping schedules to account for demands and energy costs. You could develop a pipe cleaning or component replacement strategy for your network. You could also develop real-time management strategies with embedded rules and controls in the software. So this is when you want to get into the complex stuff, but today we're going to focus on the fairly simple subdivision type of water reticulation design. So, like all the software in the Three Waters trilogy, it's a linked node model. There's probably no practical limit to the size of the networks. It's very fast. Most of the runs I've ever looked at have been, less than a second, maybe up to a second. So you can model every deflection, house connection, reducer, valve, every component in your network without detriment. You can easily have 100mm long pipes in this. So, all of these deflections that you'll see in the system you can model. And the nice thing, without any excessive simulation run times. So links, I'll get onto a live demonstration soon, but links are elements that can change the flow. So they'd consist of pipes, fair enough, pumps and valves. So the valves that we model as a link, special valves, so things like pressure reducing valves or pressure sustaining valves or throttle control valves or flow control valves or things like that. Stop valves and gate valves are handled in a very simple manner. Okay, so our nodes are sources of inflow or outflow from the network. So we have reservoirs and tanks, essentially the same thing, except a reservoir is an infinite supply of water at a predominantly constant head. A tank adjusts the head in the network depending on the hydraulic conditions. So the tank will empty and fill subject to different hydraulic constraints. Okay, so our network must contain at least one tank or reservoir, and it must contain at least one pipe. So other than that, no restraints. The dynamic water supply module has all the features you'd be used to if you're doing stormwater design. So all of the stuff that's normally in the drainage network editor is present in the dynamic water supply module. So doing things like setting pit types and pit sizes and positions and orientation and interacting with the design strings so you can actually build the network, lay it out and build it, are all sort of standard components. The way you name pits on order or type or string name, the way you lay out pipes geometrically and grade them, setting up pipe types and sizes, their orientation, how they connect to junctions, plotting of plans and long sections using the 12D CAD tools, importing and exporting spreadsheets, custom reporting of drainage attributes. All these things have been covered in other webinars and training notes. So while they're incredibly comprehensive, I'm definitely not going to attempt to repeat them here. So we're going to look at a simple project, so I might just start up a project. So what we've got here is, so what we're going to start with is a drawing that will become part of a subdivision submission. So this is an AutoCAD drawing that we got from a client who is ready to submit this for a water supply design. So what we've done here is we've taken the AutoCAD drawing and we've taken out the drainage string, which is basically that green line to the north or northeast of the system. That's the start of the drainage string. And we've converted it to, it's a super string, and we've converted it to a drainage string. So I'll start with a conversion to the drainage string. So this is our network. Okay, so if it's been created properly, all the pipes will be snapped to a pit and you'll have a contiguous network. In this example, it wasn't, so it took probably half an hour, I suppose, to reconnect everything. So that's why I'm not going through it from scratch. Now, the dynamic water supply differs from our other water-related modules in that each 12D model can only contain one network. One advantage of that is when you try and run it, it'll tell you where there are any disconnects and allow you to go and find them immediately and reconnect them. So where you have a line that doesn't have, where another line is coming in but there's no manhole on the parent line, you can create the manhole, snap to that. Where snaps missed by 50 millimetres or something because they were just drafted, you can create those. So once we've got our drainage network in, we'll open up our drainage network editor. So we can go down to our network editor under design, drainage sewer, I should say drainage sewer water supply now, and network editor. We'll pick our network, and this would be the drainage network editor you're all fairly familiar with. The hydrology methods that we support here are none. The rational method for steady state stormwater, ILSAC's, SES, EPO swim, and a New Zealand SES method, part of the dynamic drainage. The water supply is the one we'll be looking at here, and sewer tractive would be the sewer design module. So once we pick water supply, our DWS prefix here just to the right is the folder where all our results are going to be stored and the attribute group where we're going to save our data. Once you pick this, we can operate in either metric or US units. If we pick metric units, because our system can handle 25 millimetre pipes or 2.5 metre diameter pipes, sort of helpful to be able to have different units, so we operate in litres per second or litres per minute or cubic metres per second or whatever. Our tins are the tins you'd be used to in the drainage network, in the, say, stormwater, for instance, which we use for cover and grading and so on. We can handle 3 different types of friction in this model, so we can use Hayes and Williams, which is the most common one for stormwater, or Darcy-Weisbach if we're modelling things for water. Darcy-Weisbach if we're modelling fluids other than water, and Chasey-Manning you wouldn't use unless you were doing open channels, so I'm not quite sure why I included that, but anyway. So that's all the global data you set. We'd also set some defaults. So for our pits, we just set our default mode type for a pit. So whether a pit is a junction, a tank, or a reservoir by default. The other data, cover modes, RL modes, cover offsets, sump offsets, and so on. And the set out data is all stuff that would be applicable to anybody that's used the stormwater modules. And then for pipes, we'd set our default roughness. So in this case, 140, we have our Hayes and Williams roughness. If we're going to try and regrade the system, we can set invert designs and so on, which are again part of the standard stormwater design. And if our default type of link, which will be a pipe, it could be a pipe, a pump, or a valve, typically a pipe. And pipe reaction coefficients and bulk reaction coefficients are only used if we're going to model water quality, so we can ignore them. Okay, so that's pretty much all we have to enter there. So really there's only 1, 2, probably 3, 4, 5, 6 fields in global. Then we go to our pit. So our main data on a pit is just all the connectivity you have when you created your network. So you have some levels for your pipes. You have cover and grate levels that we use for clash detection and for cover requirements. And then we have an extra tab here now, which is a water supply tab. Okay, and here we have our pit type. So this is just a deflection, this pit type. We have a demand. So a demand is where water can enter or leave the network. So a demand would be where flow is going to, say, a house connection. A negative demand would be a source of inflow to the system. Rare, but you can model it. You can also vary the demand with time, which we're not going to do. And the emitter value over there is for sprinklers, which we're also not going to do. So here, all we need to enter is a demand, which can be any numeric value, 0 or positive or negative. That's all the data we have to enter for our pit. Quality, we're not going to look at. If we were going to do quality, we'd enter quality information down here, but we're not going to handle that, to look at that today, so no need to enter anything there. For our pipes, we have our invert levels, which come from the connectivity of the network. We have a shape. The only shape we support is circular, and probably not likely to support any others. We have the diameter of the pipe and the length of the pipe. Now, well, and the number of, which is always 1 in water supply. If you wanted to create 2 parallel pipes, just draw 2 parallel pipes. That's better for flash detection and so on. Our length is calculated from the network, but if you're bringing in a schematic network, we can override that with the hydraulic length, which is, as somebody's keyed in as a field. But normally that would come, so as a pit gets moved, the length gets updated. The other properties we can include here are we can overwrite the default roughness, or we can add minor losses to account for bends and so on in the system. So that's pretty much all the data that we have to enter. So that was a demand on a node, and the diameter of the pipe. Fairly simple. The water supply specific stuff, okay, is only the initial status of the pipe. So if we leave it blank, it's going to treat the pipe as open, so it's going to allow flow in either direction, so positive or reverse flow. We can close it, and that'll prevent any flow, so that would be like a gate valve or a stop valve being closed. And we can have a check valve, which will only allow flow in the positive direction, the direction you've defined it. Pipe reaction coefficient is again only relevant if we're going to do water quality, and we're not, so we can ignore that. So yeah, that's pretty much all the data. So here we have an initial status, which we're going to ignore. We'll have a diameter, which has come, and lengths and invert levels, which have come from our connectivity. On a pit, we're going to have a demand, and we're going to have surface and subsurface invert levels, which again have come from our connectivity. I'll cover tanks later, but right at the moment, this would only be if you're going to put in a depth volume curve for a tank. So let's leave that go for the moment. I mentioned in the introduction that we also need to have at least one tank or reservoir in the system. So in this case, we have a reservoir up to the northeast. So if I pick that one. So you can see here that this is a reservoir. We have a allow or maximum head water level of 137 metres there. We could vary that with time if we wanted to, but we're not going to. So that's our reservoir data. In fact, I think in this model we might have two reservoirs. So we have a second reservoir here. So that's our second reservoir with a head of 136 metres. So now we're going to run the analysis. So I'll just hit analyse. We can create the parameter plot file. We can use parameter plot files to create annotations for our long sections and cross sections. We do have some water supply runtime settings that we can tweak if we want. We're going to run a 24-hour simulation here just to show you what it's like, but because we don't have any patterns, it's all going to be just constant. Our hydraulic time step is going to be 1 hour. Our quality time step would be 5 minutes. If we had any rules, that would also be 5 minutes. Then we have things for patterns, if we're having variable patterns, and start clock times and tolerances and trials and various things. But generally you can just use, well, in fact, I think I've always used all the defaults. So if we hit run, it'll run the simulation. It's finished. Yep, it's told it's finished. It ran in a couple of seconds, but most of that was spent in our in reading attributes in. If I go back to the editor now, where were we before? Down here somewhere. Let's just have a look at this line. Now if we go to results, we're going to look at the time series results here. So for nodes, we can look at demands, elevations, pressure, quality, a dynamic plan, or let's just go for all node results. That's a wee bit small, we might just change that a bit. I'm running on a fairly high resolution monitor here, so I'll just save that as the default and resize it. Okay, so here you can see we have the head at the node, the demand, so demand is about 60 or 70 litres per second. The pressure in the node, if there was a chemical analysis, it would show us there, and the status of the node. We can also show things like dynamic plan view, so we can, I'll make this bigger as well. So we're looking here at pressure and flow, so we can look at throughout our network, we can see minimum, maximum values of pressure and flows, and we can step through it with time. So I can go to the next time step. The next time step. Unfortunately, it's not going to change because this doesn't have any patterns in it, but you get the general idea. And the sort of data we can turn on there are heads, pressures, demands, quality, status, flow, velocity, head loss, status, friction, settings, so on. So a fair bit. Just close that. And for a pipe, I'll just go to all link results. Same problem. Okay, so here we can see our upstream and downstream heads. Setting in this case is the roughness of the pipe. If you're using one of the other methods, it can change with the hydraulics. The head loss, the friction, status, flow and velocity. That's the data we can look at. We could also look at all the attributes. The graphical attributes. So if I turn on water supply labels, you can see here we get our demand, our head, minimum, maximum heads. So the parameters that we can choose from here are, for the nodes, we can look at demands, heads, pretty much the same things we saw in the graphs, pressures, quality, and minimum, maximums, and average of those. For links, we can look at flows, velocity, head loss, friction factors, quality parameters, status, link settings, and so on. And again, minimums, maximums, and averages. Pumps, we can also look at things like energy usage, cost of energy, and so on. And for links, we could also look at things like the reactions, water quality reactions and so on, but we're not going to get into any of that. That's all the simple stuff. So pretty much that's all you had to do for your network. So I might just turn those off because they've cluttered things up a little bit. So you can see in our network, well, you might not be able to see in our network, but we have a valve here, we have deflection here, we have a water supply meter. We have another stop valve, we have a gate valve, we have a deflection. These pipes are only 50 millimeters in diameter, I think, so you can see they're fairly short connections between them. Now, if you want to have a look at the 3D view of this, which I think I might have started up with, you can see we've got a number of valves throughout the system. You could, if you were keen enough, show every deflection, every valve and so on, and what the actual component looked like. Bit of overkill for me, so I certainly didn't try and do that. One of the other nice things we can do with the water supply, there's probably the most common package around is a public domain one called EPA-NET, and people use it to create a schematic network. So for this model, the actual analysis was done using EPA-NET, and then it was all drafted up in AutoCAD. So if I want to import an EPA-NET file, I can, straight to it. Okay, this is an EPA-NET file that they use to run their analysis. So it has the junctions, tanks, pipes, so on in it. If I want to import that, I can just drag and drop it. This was originally written for swim input files, but EPA swim input files, but extended to account for water quality network files. Sorry, water supply network files. So if I create that, it'll create a model. Finish that. I'll go into turn it on. So we just created that one. So this is actually the same model, but it's the schematic network that they used. So we were looking at, this area here in our analysis. This model's got maybe 40-ish elements in it. One of the things I did notice when I was doing this model is the line, the almost vertical north-south line here wasn't included in their final design. So they analysed it with it, but then didn't include it when they put in their submission. So, yeah, who knows how accurate the submission is. Hopefully pretty good. But now when we've brought that in, we can also go and open up our drainage network editor, pick this network. The output window is telling us that we've got a loop in the system. Not such a bad thing. In fact, I'd hope we'd have lots of loops, so we can pretty much ignore that one. We go to analyze, we'll run it. Yeah, simulation finished. Come back here and have a look at our results. Different model, so it has different defaults. Okay. Okay, so that's how we'd bring in an existing model. If we're doing, just briefly touch on some of the more sort of esoteric elements. This is a really simple schematic model. In this one, we've got a reservoir here. So this is our reservoir. We also have a pump. So a pump curve can be a single point pump curve, a multi-point pump curve, a 3-point pump curve, variable speed pump. And if you don't like any of those, you can just put in how many horsepower your pump is and it'll generate a curve that hopefully fits it. So the initial status of the pump can be on or off, it can be open or closed, running or not. We can adjust it with a speed factor. These are all optional. We can have an efficiency factor if we're working out the energy usage. We can have a cost of energy. We can have, if the cost of energy varies with time, we can put that in. We can have a speed pattern, so our speed varies with time. Our efficiency can vary. There's a lot of things you can do which you don't necessarily need to on your simpler model. It's also got, this one hasn't got a valve. But your valve types can be pressure reducing, pressure sustaining, breaker valves, flow control valves, throttle control valves, and general purpose valves. So lots of different valves. We can control them. If I go back to global, we also have rules and controls that we can use with pumps. So link 9 is the blue link on the left of the screen. That's our pump. So we can say it's open if the node 2, our tank, falls below 110 metres. It closes if it gets above 140. So we'll only pump under those conditions. We can have fairly complex rules, which I don't have any. Hang on. Let's see if we've got another one. Okay, let's just pick this one. So we can also have rules. So, if the level gets above 19 and the pump is closed and a valve is open and the clock time and it's after 8 AM and it's before 6 PM and the tank level is this, and we can have quite complex rules, if we want to analyse the system. But again, these are all things you don't have to do, and in fact, most of the time you wouldn't do. But if you need to, it's available. I think that pretty much covers what I wanted to go through, so I might just ask Lisa if there's any questions.
Thanks, Jeff. Yes, we have got time for some questions. We've had a few through. So John in Brisbane asked, what's the minimum amount of work to create a model?
Yeah, okay. I guess this last bit was a bit like drinking from a fire hose, so we'll go back to the start again. Okay, our simple, in our simplest state, all we need, the pipe physical data that you would put in for your submission and a demand. If you have any, wherever your demands are, so your firefighting demands or your regular house connection demands, you'd put in at the node, and you'd need at least one tank or reservoir in the system to provide water. So that's all the data you have to enter. That's all the mandatory data.
Sure, okay. Now, I might have missed something, but I was wondering along the way what modules you'd need for this option.
Well, you'd need the drainage module for the drainage network editor, but other than that, the only other thing you need to show everything I've shown is the dynamic water supply module.
Sure, okay. A couple of people asked, what size network can this handle?
Okay, there's probably no practical limit. I mean, it's fairly efficient with memory. This model, the schematic one I showed, had roughly 40 nodes in it. This model, I think from memory, has got about 350 links and 320 nodes or something. It handles that very comfortably. You could easily go to 10 times that size without any concerns, and possibly even 100 times that size. So, yeah, much bigger than your brain can probably handle. So, big networks.
Sure. Jenny in Melbourne said most subdivisions will break into an existing network. So how do we model that?
Oh, yeah, good question. I didn't mention that. Okay. So this is a subdivision design. So, yeah, it would have been breaking into an existing network. So obviously we don't have a big dam up here at the, where we're breaking in. So the way you would handle it is your water authority will give you a pressure that they can sustain at a particular node in the network. So in this case, up to the top middle of the screen there would be one break-in point, one tie-in to the existing network, and they said that had an elevation of, I think from memory, 137 metres. And then they had a second tie-in, because you like to have a loop system where you can, down here, and it had a sustainable pressure of 136 from memory. So although we've called them reservoirs, they're actually the tie-in points to your existing network. Yeah, hope that answers the question.
Okay, we'll just take one more. Sort of a bit more of a comment than a question, but I think you might be able to expand on this concept. Peter from Queensland commented, in the original subdivision model, the 3D view showed valves all over the place, but you didn't mention any of the data you'd need to enter for them. You said all you needed were pipes, demands, and one reservoir or tank.
Okay, yeah. Okay, the valves that we talk about when we talk about controlling flow are specialty valves. So they're things like pressure sustaining valves or pressure reducing valves or pressure breaker valves and things like that. The most common valves you have in a drainage network would be stop valves and gate valves, and that's pretty much what I think all these are. So we have a drainage network here that is predominantly stop valves and drainage valves. So let's just turn on the... I can't remember which model it is. Okay, oh sorry, there they are, okay. So these are our valves here. So the way we'd model those is we'd go to our pipe where the valve was, we draft it by telling it the pit type as a valve. So when it displays it on the screen in 3D, it shows it with whatever pit type we've selected here. So that's why you're seeing the valve. So it's a 100mm valve. Okay. When we analyse it, the valve if it's a gate valve or a stop valve, the valve is just treated as a pipe, and it has some status. So it's either opened or closed. So if it was a gate valve and it was fully opened, we'd just say the pipe was completely open. If it was a gate valve and it was shut, the pipe was completely closed. We could, I briefly mentioned rules. We could control the open and closed state of that valve with rules if we wanted to. So we could say if a water level got below a certain amount, then close this valve, or, you know, but we actually control the pipe status for a stop valve or a gate valve. But normally this is what you would use to, if you're going to do some sort of component replacement, you just come here and close off that valve and then analyse it again and see what your system looks like. Yeah, so that's pretty much it. I think I'm running over time, but I'll see if any Lisa's got.
Great. Yes, no, we will finish that off there. Thanks, Jeff, and thanks to the audience for your questions. Sorry to anyone we couldn't answer live, but we'll get back to you individually afterwards. The recording of this webinar will be available in coming days through our website and our YouTube channel. Our next two Industry Solutions webinars are Underground Storage Tanks on the 5th of April and Road Flow on the 20th of April. I can see there's a bit of a Three Waters theme happening in this series at the moment, so I hope you'll enjoy that. We've also got some great training topics coming up, so we'll keep updating the website with those as they're set and keep you posted through email and social media. And if you need to contact us in the meantime, you can always go to our website and I think, look for all those topics and everything on there. That concludes our presentation for today. Thank you for attending, and we hope to see you at future webinars.